This is the solution to problem 415 of Halliday, Resnick, and Walker. Let's go look at the problem. So we're told that particle is sitting at the origin, but it leaves with an initial velocity given by that value. And then it says there's a constant acceleration. Notice, though, the acceleration exists both in the x direction and the y direction here. So it's not just a simple projectile motion kind of a problem. Now we're asked, it says here, when it reaches the maximum coordinate, what's going on in terms of its velocity and its position. So let's go on. The first thing, of course, is to draw a coordinate system. So we'll set up positive x to the right and positive y up. And then what's happening is that we're starting at the origin, but there's an initial velocity. So we can draw that initial velocity vector there. And then we know that we've got the acceleration going on. It's a negative acceleration in the x direction. So that means that velocity that starts off positive is going to decrease. So we start moving off to the right in terms of the x component, and it'll eventually turn around and head back in the other direction. So we sort of know that's what happens when the acceleration is in the opposite direction to the velocity. Now in the y direction, we start off at zero velocity, but we are heading off with that negative acceleration, so we pick up speed heading down that way. We could try to draw some approximate picture of this motion here. We start off heading this way, but then we pick up speed in the negative y direction. Eventually the x value turns around, looks something like that, I suspect. Good idea to sort of think about that a little bit. Sometimes these things get a little complicated, but I think that's worthwhile sort of at least drawing that picture and thinking about it. All right then, so what do we need to work this? Well, clearly we have constant acceleration in both x and y, so we can write down these various relationships. In the x direction, again, we start at the origin, so there's no x0 that comes in there, but that's the v0x and the a sub x times t. We can also write down a similar equation for the x component of the velocity with the acceleration. In the y direction, it's similar, except that, of course, we're starting off with no initial y velocity, so it's just the 1/2 a sub y t squared. And then the y velocity also is a little bit simpler because there's no initial value. Notice I've just used symbols ax and ay here, and we know that those are going to be negative because the values are negative, but I haven't explicitly put those minus signs in. We'll just wait for the minus signs when we actually put numbers in for these. All right, so those are the equations we're going to use. How do we determine what where this maximum coordinate shows up, or when the maximum value of x? Well, remember, this is a calculus sort of idea that the maximum of a function is where its derivative is equal to 0. But of course, from a physics perspective, it kind of makes more sense than worrying about the calculus aspects. If we start off over here and we slow down, eventually we turn around, it's pretty clear that the velocity has to be 0 at that maximum point there because it's positive and then it changes over and starts being negative. So this is a result from calculus, but it's also a result that we know from some basic physics. So all we need to do then is we want to figure out what that value of T max is. So we'll just put this equation down there again with T max, and then it's just a matter really of solving for T max. So move that over the v0x to the other side, and notice, as I said, the a sub x is going to be negative, and so that will combine with that negative to give us a positive value of the t of the time. So let's just put those numbers in. 3 meters per second divided by the 1 meter per second squared gives us a plus 3 seconds for the time at which that occurs. So that's the time at which that happens. Now what we're actually asking for here, or what we're asked for, is what's the velocity at that particular time. So basically we just have to go back to the equation for the velocity and the equation for the velocity in the y direction and plug in that value of t. So in terms of the x component, we just plug in the value of t max, and we'll plug those numbers in. And you work that out, and of course comes out to be 0, which is not a big surprise. In fact, it better be the case because, after all, we solved this equation for T max with the expectation that it was giving us a 0 value for the velocity. So, sure enough, we get 0 down here for the x component of the velocity. The y component, we'll take this expression here and we'll plug in T max. And so when we do that, put in various numbers, the minus 0.5 meters per second squared times 3 gives us a velocity of minus 1.5 meters per second in the y direction. So that's heading directly down. That's kind of what we expected if we go back here and remember our little path. Right at this particular point, the x component velocity was 0, but the y component clearly is not going to be, and so it's this velocity that's headed strictly downwards like that. All right, so that's the velocities. That's actually the answer then to part A. Now we're also asked, where is this thing at that particular point, at that particular time? So it's really just a matter of going back to the equation for x of t and y of t and putting in the value of t max. So it's pretty straightforward, I think, here. X of t max, we use the equation up there and plug in the value of t max. If you put in the various numbers, not too complicated to sort of work that out, and the answer there comes out to be 4.5 meters. If we do the same thing then with the y of t, plug in y of t max, 1/2 a t squared, put in those numbers, and that comes out to be a negative, as expected, minus 2.25 meters. So notice actually we're done because the problem asked us for the displacement or the position vector at that point. And we worked out the two components. This up here is the x component, and this is the y component. And if you're asked to specify a vector, given the two components is really all you need to do. So unless the problem specifically says find the magnitude and the direction, having the components is good enough. Now we could go ahead and draw that if we wanted to, that position vector 4.5 units over in the x direction and then minus 2.25 down. So there it is, more or less where we expected it to be. And the velocity vector is then headed, at that particular point, is headed directly in the negative y direction. So again, if we wanted to, we could sort of think about what that curve looks like. And if we wanted to do something fancy, you could use your graphing calculator to try to sort that out. But as I said, we're really done once we have those two components, the x and the y components.